Hello again. From this video, we will start to discuss how to design a controller. But before we start, some techniques in designing a controller for a specific system, I want to give an introduction first on how and what controller can do. Now let's consider the following system. So you have a dynamic system. The objective of a controller that you are going to design is to alter, to change the dynamic behavior of the system that you have without touching the system itself. So let's consider now you have a dynamic system. Let's consider a DC motor. And if you have a DC motor, you want to run the DC motor should always be equipped with a power supply or an amplifier, right? So you have both these two systems, a DC motor and an amplifier, but apparently after you run it, your DC motor together with the amplifier does not behave dynamically as what you expected. Let's say your DC motor apparently exhibits a very large steady state error when you want to run the DC motor at, let's say, 1000 RPM, but apparently after you run it and then you let it run until it reaches the steady state condition, your DC motor only run at 950 RPM. So there is a steady state error of 50 RPM. That might be one case, or there might be also another case when your DC motor can deliver a very small steady state error, but in order to achieve the desired steady state error, apparently your DC motor takes quite a long time. You have to wait for minutes to have your DC motor to respond to what you want. So of course you don't like this DC motor. You want your DC motor to respond faster, or you want your DC motor to exhibit a less steady state error. But of course you cannot change your DC motor. The only way, if you want to improve the performance of the DC motor directly, you have to probably, again, just an example, you need to change the magnetic core of your DC motor with another component with a strong magnetic field, or you might want to change the coil of your DC motor. In some cases you don't want to do that. So what we can do, we put your DC motor, of course, together with your power supply in a closed loop form. How do we do that? Because we cannot change anything in our DC motor as well as in our power supply, what we can do, we close loop it, we measure the output, the rotational speed of your DC motor using a sensor, we close loop it, and then we put a controller, a desired design controller, in order to make your system to respond as what you expected. So our objective here, we need to design a controller here to change the behavior of your system without touching the system itself. Okay, so what we are going to do, we will design a controller. Of course, design of the controller has to respect some rules. First thing that I have to mention here, because you are going to design a controller, same like if you are a fashion designer, you have to specify the requirements of your controller. In this slide you can see the mind maps on how we design a controller. In the very first step, you need to define the objective of your controller. The objectives of your controller. It might be your requirements are you want to have your DC motor to have a low steady state error when I give a step input. You might also have different requirements, and one of them could be that you want to have your DC motor to have a minimum steady state error to RAM input. Or you might also have another requirement that you want to have a DC motor, a controlled DC motor with smaller time constant so your system can respond faster. You might also want your system to have less overshoot. Or there might be also a case when your system is initially unstable and you want to stabilize your system. So this is a few things that you have to define in advance before we start to design the controller. The design of the controller itself, we can do it by different means. We can design it in time domain, we can design it in Laplace domain, we can design it also in frequency domain. Probably without you realizing it, we have already discussed long time ago how to design a controller using time domain approach. I will give a clue again to you later on how we design a controller in time domain, because actually you have already done it before. Laplace domain is another means of designing a controller, but we are not going to discuss it in this topic. We are not going to discuss it in this video. Just to give you a clue, when you want to design a controller in Laplace domain, you can do it using a root locus method, but we are not going to discuss it in this topic. What we are going to discuss in this topic in the next few short videos, we are going to design a controller using frequency domain approach. Okay. In parallel, if you want to design a controller, you need to understand the behavior of the system that you want to control. At the same time, you need to be able also to represent mathematically the controller design. And how to represent it? There are many ways to represent a dynamic systems, like what we have already discussed in the previous videos. We can represent a dynamic system in differential equation form, in a state space form. I have to mention that we don't really discuss this in this topic, but we also have discussed transfer function representation, and we also have discuss O0 and Bode plot representation. This is something that we just discussed in the previous few videos, right? Once we know the model of the system, you have already predefined the objective of your controller. What do we have to do next? We are ready to design the controller. And designing a controller can be carried out using many different tools. We can do it using a state space tool, but we are not going to discuss this in this topic. We can do it in Laplace domain, as I have already mentioned before, and the tool to design a controller in Laplace domain is by using a root locus, but we are not going to discuss it also in this topic. What we are going to discuss in the next few videos are designing controllers in a frequency domain using loop shaping technique. Apart from these three main tools to design a controller, We have already discussed it also a long time ago when we discussed about stability. You can also use route Hurwitz technique to design a controller, but it is restricted only to design a controller to stabilize a system. There are also many more tools to design a controller. Cohen-Kuhn, Ziegler-Nichols, and many others. Those are some tools that we typically use in practice to design certain controllers. But again, we are not going to discuss these last few tools, Cohen-Kuhn and Ziegler-Nichols and everything there. These are more advantageous when you are designing a controller in practice. What we are going to discuss in the next few videos, we will focus mainly on loop shaping technique. Okay, let us start with the very first practice on designing a controller. The first controller that we are going to discuss and also to design is a proportional controller. You still remember in one of the videos that we have already discussed before, there are many types of controller. Proportional is one of them. Proportional integral, proportional derivative, or proportional integral derivative of, or we normally abbreviate it as PID controller, and so on and so forth. We will start it with proportional controller now. Let us consider now a unity feedback system with a proportional controller. What is proportional controller? Proportional controller is a controller that only contains a scalar value on it. So as a system itself, a proportional controller is a static system. There is no access in your controller there. And this proportional controller, at this moment, we are going to use it to control a system where the transfer function is equal to GS in a unity feedback form. Okay? If we take a deeper look on the Bode diagram of the open loop transfer function of this unity feedback system, the proportional gain in our proportional controller, Kc here, because again Kc is a scalar value, the effect of introducing proportional gain here, if you change the proportional gain here from, let's say, initially you haven't tuned your proportional controller, you haven't tuned the proportional gain Kc, so initially, let's say Kc is equal to 1. What is the effect of Kc? To the magnitude, if you introduce certain proportional gain in this controller, the magnitude plot in the Bode diagram of this open loop transfer function will be like this. So now by introducing Kc, if initially you said you haven't tuned the Kc, you haven't tuned the proportional controller, so initially Kc is equal to 1. After you introduce Kc, after you tune the Kc, the effect of Kc to the magnitude plot in the Bode diagram will be like this. Your new magnitude plot of the open loop transfer function will be equal to Kc times Gs, where Gs is the transfer function of the open loop transfer function in your unity feedback system before you introduce the controller. What does it mean? Of course, the magnitude plot of a Bode diagram is always represented in dB scale. So if I represent this magnitude value in dB scale, the magnitude value will be equal to this in dB scale, right? What does it mean? This means your new magnitude plot of your Bode diagram in your open loop transfer function will be shifted vertically by 20 log kc. If initially your open loop transfer function is gs, so initially the magnitude plot is just simply 20 log gs. After you introduce kc, the magnitude plot of your Bode diagram will be equal to this one, 20 log kc plus the original magnitude value, which means again the introduction of kc here will shift your magnitude plot vertically according to the value of kc, right? Of course, if kc is greater than 1, the magnitude plot will be shifted up because 20 log kc will be positive. If your kc is between 0 and 1, your magnitude plot will be shifted down because your 20 log kc will be negative if kc is between 0 and 1. That is the effect of proportional gain kc to the magnitude plot in your open loop transfer function. What is the effect of kc to the phase plot? Now, after you introduce kc, your phase value will be equal to angle of kc plus angle of gs, right? That's the property of a complex number. If you have x times y and both of them are a complex numbers, the angle of x times y is equal to angle of x times, plus angles of y. That's the property of complex number operation. So again, same to this one, the angle of kc times gs will be equal to angle of kc plus angle of gs. But kc is a scalar number. Kc is real number. If you have a real number, the angle of a real number is equal to 0. This means then, after we introduce proportional gain kc, the phase plot remains the same. In short, proportional gain will only vertically shift the magnitude plot. It does not alter the phase plot of your open loop transfer function. Okay, so that is the basic principle of proportional controller. Now let's take a look on what proportional controller can offer to us. Let's consider again the story of steady state errors. If initially, let's say, to this unity feedback system, I haven't tuned the proportional controller. So the proportional controller, initially the kc is equal to 1. Just leave it as a default value before I tune the proportional controller. So kc is equal to 1 initially. When kc is equal to 1, the steady state error of this system will be equal to this one, right? We have discussed this in the previous videos. This will tell us the steady state error for a certain input R here. Depending on what the input, we should be able to calculate the steady state error. Now to the same system, before we adjust the proportional gain kc, if we have a type 0 system, so consider again we have a unity feedback system, but this unity feedback system is considered as a type 0 system. What does it mean? If, I hope you still remember about system type matters there. If we have a type 0 system, the steady state error to a step input, so if we give a step input to this type 0 system, the steady state error will be, using this equation, equal to limit s to 0 1 over 1 plus gs, or it will be equal to 1 over 1 plus kp, where kp is static position error constant. You still remember on our discussion of system type. That means, of course, then in this case our kp, our static position error constant, is equal to limit s to 0. Please bear with me, I'm writing it with my mouse. Limit s to 0 of gs. Right? So again, if I have a type 0 system, the steady state step error, or the steady state error if a step input is given to the system, will be equal to 1 over 1 plus kp, where kp is equal to this one. Right? Now, if we have type 1 system, for type 1 system, you still remember that discussion also? If a RAM input is given, the steady state error to the RAM input will be equal to limit s to 0 1 over sgs, or equal to 1 over static velocity error constant. Right? Where again here kv, static velocity error constants, is equal to limit s to 0 times sgs. That is for static velocity error constant. Now if we consider type 2 system, if a parabolic input is given to the system, the steady state error to this parabolic input will be equal to limit s to 0 1 over s square gs, or it will be equal to 1 over static acceleration error constant, where ka here same like before. Our ka now pretty similar to what we have already written before. Limit s to 0, but now is equal limit s to 0 of s square gs. Right? So to type 0 system, kp is equal to limit s to 0 gs. For type 1 system, kv is equal to limit s to 0 sgs. For type 2 system, ka is equal to limit s to 0 s square gs. This will happen before I tune the proportional gain in my controller, when initially the proportional gain kc is equal to 1. Now let's consider after I tune the proportional gain kc. Let's take an arbitrary number. The proportional gain now is equal to kc. Kc is a value that I have already set to my proportional controller. With the same analogy then, to this new system with a certain kc, if I have type 0 system, my steady state error to step input will be same like before. Limit s to 0 1 over 1 plus the open loop transfer function, but now my open loop transfer function is equal to kc times gs. While in the previous case, when before I tuned the proportional gain, Kc is equal to 1. So in the previous case, the steady state error to the step input is equal to limit s to 0. Let me go back to the previous slide. Limit s to 0, 1 over 1 plus gs, because at that moment the open loop transfer function is just simply equal to gs when kc is still equal to 1. But now my kc is any arbitrary number after I tune the proportional gain. Therefore, my steady state error because of the step input will be equal to limit s to 0 of 1 over 1 plus the open loop transfer function kc times gs. Therefore, my new kp will be equal to, my kp new now is equal to limit s to 0, limit s to 0, right, kc times gs. This is my new kp. Similarly then, for type 1 system, this will be my new steady state error because of ramp input, and my new kv now is equal to limit s to 0 s times the open loop transfer function now, because I have kc, so kc times gs. For type 2 system, of course, we can take the same story. My new ka now is also equal to limit s to 0 of s squared. It's not easy to write with my mouse. S squared kc times gs. Okay. What does it mean? Depending on the type number, whether it is type 0, type 1, or type 2, if I want to improve the steady state behavior, steady state performance from 1, let's say if we are talking about type 0 system, if I want to improve my kp in my type 0 from the old kp to the new kp, I should be able to define how much kc that I have to set, how much the proportional gain that I have to set. If initially for my type 1 system I have a certain old kv, but then now I have a requirement to improve the steady state performance, in such it will have a new kv, so I have to set a proportional gain in my system to be equal to kc according to the new kv. Same thing to type 2 system. Therefore, if I have type 1 system and I want to improve the steady state performance in terms of kp from initially the kp is equal to the old kp, and then the new system should have certain kp, new kp, then that means I just have to simply introduce proportional gain in my controller equal to kc, where kc is equal to the ratio between the desired kp, the new kp, and the original kp, the old kp. Same thing if I have type 1 system, and then this type 1 system has initially has a certain kv, an old kv, and then I have a requirement to improve the steady state performance to have a new KV, so I just simply have to introduce proportional controller with a gain equal to Kc, where Kc is just simply the ratio of the desired KV to the old or the original KV. Same thing happens to my type 2 system, right? The Kc that I have to introduce, the proportional gain, proportional controller that I have to introduce to my type 2 system if I want to have to improve the steady state performance of my system with respect to a new Ka, so I have to set a proportional gain equal to the ratio of the desired Ka, the new Ka, to the original Ka, the old Ka. Okay, let's take a look on an example to have a clearer picture on this proportional controller design. Let us consider a unity feedback system, as you can see in this upper right corner of this slide. And originally, this unity feedback system has a open loop transfer function equal to this form, 10 over s plus 4. Before I set the proportional controller, before I tune the proportional gain, what will happen? As you can see, initially Kc is equal to 1. If you take a look on this upper right corner of this slide, Gs is equal to 10 over s plus 4. This means in the open loop transfer function, I will only have one integrator, one single s in the denominator. What does it mean? This means I will have type 1 system, right? This is a type 1 system. If I have type 1 system, I should be able to analyze the static velocity error constant. The static velocity error constant Kv, originally, this is the old Kv, the original Kv. Based on the formula, this should be equal to limit s to 0, right? S times the open loop transfer function. But initially, I haven't tuned the proportional gain, so the open loop transfer function is just simply equal to Gs. If I substitute this Gs to that Gs, so this S will cancel. Let me change the color first. This S will cancel this S. At the end, I will only have limit S to 0, 10 over S plus 4. Then this will be equal to 10 over 4. 10 over 4 is equal to 2.5. Exactly what it is mentioned in this slide. The original Kv, or let's call it Kv1, is equal to 2.5. This means if you have a type 1 system with a static velocity error constant equal to 2.5, the steady state error to a unit ramp input will be equal to 1 over static velocity error constant. That's how we calculate steady state error to a unit ramp if the static velocity error constant is known, right? So 1 over 2.5, then it will be equal to 0.4. That is the performance of my original system before I tune the proportional controller. But apparently I don't really like the behavior of this system. A steady state error of 0.4 to me is too high. And then I want to design a controller in such the steady state performance will be improved. Improved by reducing the steady state error from 0.4 to 0.2. So that is my requirement, the requirement that I set before I design my controller. I want to have the system to perform better in the steady state condition. The steady state error should drop by half of it. That means having known the desired steady state error, I can eventually calculate what is my desired static velocity error constant, because steady state error is inversely proportional to the static velocity error constant. So I can find Kv2, the new Kv, should be equal to 1 over the desired steady state error, 1 over 0.2, which is equal to 5. So this is my desired Kv, desired static velocity error constant. What do we have to do? Then we just simply have to introduce proportional controller. We have to tune the proportional gain. From the previous slide, we have already discussed that if we want to improve the steady state performance, we just simply have to introduce, or we have to tune the proportional gain there to be equal to the ratio of the desired Kv with the original Kv. The desired Kv is 5. The original Kv is 2.5. That means the proportional gain that I have to set in my unity feedback system is equal to 2. 5 divided by 2.5. We discussed at the beginning of this video, introducing 2 gain of 2 in our proportional gain means it will shift up the magnitude plot by 20 log 2, right? 2 is greater than 1, so the magnitude plot will be shifted up by 20 log 2 without changing the shape of the phase plot, right? Let's take a look on how the Bode plot will look like in the next slide. So at the beginning, before tuning the proportional gain, when initially the proportional gain is equal to 1, more or less the Bode diagram will look like this. The upper one is the magnitude plot, the lower one is the phase plot. And then what will happen? We can estimate also from this magnitude plot what the static velocity error constant is. We have already discussed it in the previous video. How to estimate static error constant based on the magnitude plot of the open loop transfer function. So if this is the magnitude plot, what you have to do, simply you just have to extend the asymptote of the magnitude plot at low frequency until it crosses the frequency axis. The frequency at which the asymptote crosses the frequency axis will tell us the static velocity error constant, right? The slope at a low frequency, the slope of the magnitude plot at low frequency, obviously because this is a type 1 system, the slope here will be equal to negative 20 dB per decade, right? So you just extend this line until it crosses the 0 dB line, the frequency axis, and then you can find the static velocity error constant. Okay, let me erase this first. What do we do now? Based on our previous analysis, we will introduce now proportional gain of 2. From what we discussed before, introducing proportional gain of 2 means we will shift up the magnitude plot by 20 log 2 dB. So the green one here in the magnitude plot here is the new magnitude plot of the open loop transfer function in our unity feedback system after we introduce proportional gain of 2. What about the static velocity error constant for our new system? Same thing, you can also analyze the new static velocity error constant by extending the asymptote of the magnitude plot at low frequency until it crosses the frequency axis, and this frequency will tell us the new KV. The new KV apparently is equal to 5. If you plot it using MATLAB or any other tools, that you will really see the value of the old KV and new KV. I probably in this slide I don't really draw it proportionally, but by any means, if you have a proper plot, you will see the static velocity error constant more precisely there. Okay, so by introducing a new proportional gain here, by tuning the proportional gain, I will shift up the magnitude plot, but at the same time I do not change the phase plot. The phase plot remains the same. I can improve the steady state performance in terms of static velocity error constant from 2.5 to 5 without changing the phase plot. But what does it mean? It has also different meaning here. If you look at this, at the beginning, before I tune the proportional gain, the magnitude plot crosses 0 dB line, crosses the frequency axis at this point, right? What does it mean? The magnitude plot crosses 0 dB line at this point. What does this frequency mean? This means this is the phase margin frequency. This is the phase margin frequency. So my the phase margin frequency of my original system before I tune the proportional gain will be equal to this omega PM 1. That is my phase margin frequency before I tune the proportional gain. Knowing the phase margin frequency, of course, then I can find the phase margin of the original system, right? So gamma 1 here now is the phase margin of the system before I tune the proportional gain. What will happen after I tune the proportional gain from 1 to 2? In the new system, my magnitude plot is the green one here. This green curve will cross 0 dB line at this point, which means again this is now my new phase margin frequency. My phase margin frequency is increasing. What does it mean? This is my new phase margin frequency. Obviously, this will mean my new system, after I tune the proportional gain, the new system will have gamma 2 phase margin. The phase margin drops from gamma 1 to gamma 2. In the one hand, of course, from the perspective of steady state performance, we love it because the static velocity error constant increases by 2 from 2.5 to 5, meaning that the steady state error will reduce. But from the perspective of phase margin, we reduce also the phase margin from gamma 1 to gamma 2. And if you still remember in our previous discussion when we started discussing this Bode plot analysis, I think in the previous 2 or 3 videos, we explicitly concluded that the higher the phase margin, the higher also the zeta, the damping ratio. The smaller the phase margin, the smaller the gamma, the smaller also the damping ratio. What does it mean? If we have small damping ratio, which means the possible overshoot will be also larger. The smaller the phase margin, the smaller the damping ratio, but the smaller the damping ratio, the larger the maximum overshoot. So we will have more overshoot in our system by increasing the proportional gain. The change of this phase margin as a result of tuning the proportional gain can be used also to as a basis in designing a controller. So there might be a case where you don't want to increase the static error constant, but instead you want to increase the phase margin. You might be able to do that by introducing a proportional controller. By tuning the proportional gain, you can also change the phase margin, which in turn will also change your damping ratio. So damping ratio can be also used as the design requirements in your proportional control design. Okay, so this is just the first step in controller design when we design a proportional gain. In the next few videos, then we will also discuss on how to design PI controller and PD controller.